we've dedicated our company's lives to advancing this form of computing to enable breakthroughs in science all over the world. And this is what GTC is dedicated to do. Well, we have a lot to talk to you about today, so let's get started. There are two fundamental forces that's shaping the computer industry today. The first is what is known as the end of Moore's Law. As you know very well, Moore's Law is propelled by three fundamental forces over the last 50 years. The first is that semiconductor physics has made it possible for us to scale transistors, making them smaller and smaller, as a result, making them faster as well as denser. By making it denser, we have more transistors, and when we have more transistors, we can apply them to improving the architecture and the design of CPUs. Over the years, we've made CPU data paths wider, we made the pipelines deeper, we invented all kinds of great technology like superscalar technology and out-of-order execution. Each and every one of those generations, we applied those transistors, the increased number of transistors, to those design techniques. Meanwhile, the frequency of those transistors continued to increase. As a result, over the course of 50 years, the microprocessor, the CPU, increased in performance by 50% per year, or twice every couple of years. While the power of something that just naturally gets faster and faster over time without you doing anything about it is really powerful. Software developers develop their software once, and every single year, that software got faster. Meanwhile, they loaded more software onto the microprocessor. As a result, features got more rich. So you either received higher performance with the same software or more functionality at the same speed over time. The computer industry advanced in that way for 50 years. And all of a sudden, over the last several years, that free ride has come to an end. Transistors got so small that essentially these switches, these light switches, are always on. To the point where the amount of leakage, sub-threshold leakage, this current that's going through that transistor, whether it's in a state of 1 or 0, made it impossible for those transistors to continue to deliver on the performance that has been promised and relied upon for 50 years. Those transistors no longer make it possible for us to increase performance without increasing power dramatically. Meanwhile, as the number of transistors continue to grow, microprocessors aren't able to apply those new transistors to new design techniques. We ran out of ideas. As a result, microprocessor architecture advancement has slowed. The transistor performance no longer increased. The combination of those two factors caused what is effectively the end of Moore's Law. While simultaneously, something else was happening. Simultaneously, this new approach to computing called deep learning emerged into the world. It's been around for quite a long time, but deep learning had a really interesting handicap. Now, first of all, what deep learning enables you to do is whenever you converse with a computer, whenever you load your photos into the cloud and it magically discovers how it ought to be sorted by the vacations you've been to, by the people that you took the picture of, somehow it's smart about collating, grouping, finding those photos for you. It's the technology that's making it possible for us to develop self-driving cars and potentially detect cancer earlier. That fundamental breakthrough has been around, as it turns out, quite a long time. And in fact, one of the most important researchers, AI researchers, was born right here in Munich. Jürgen Schmidhuber was one of the earliest researchers to have started to work on artificial intelligence and artificial neural nets. And he was one of the first to apply GPUs to deep neural nets. And his lab was able to win the road sign detection contest. His lab also was one of the first started to use recursive neural nets, recurrent neural nets, and created this new idea called long-term, short-term memory. This neural net architecture that's making it possible for us to detect sequences and recognize speech. That was done right here in Munich. Well, this deep neural net had a handicap, and this handicap was, in order for this deep neural net to be effective, it needed an enormous amount of data. It needed to train these layers and layers and layers of neurons and synapses inspired by the human brain. It needed tons and tons of data to train this network. Otherwise, it was overfit, or otherwise known as ineffective. Well, in order to train this neural net with huge amounts of data, you need to do huge amounts of computation. Trillions and trillions and trillions of operations necessary to effectively, for this neural network brain, to learn how to perform an intelligent task, like image recognition or voice recognition. Well, that handicap was overcome with the discovery of the GPU. And so these two factors, the end of Moore's law and the emergence of a new software development method, a new software technique, happened almost exactly the same time. And these two dynamics turbocharged the adoption of GPU computing. This form of computing we've been working on for literally a decade and a half. In fact, you could say that ever since the founding of our company, we've focused on only this form of computing. No company of our scale and size has ever dedicated itself to this one singular field of computer science. GPU accelerated computing was all we do. Now, as a company of 12,000 people, we've now dedicated and invested some close to $30 billion in the pursuit of advancing GPU accelerated computing. Well, if you look at the chart, if we're able to turbocharge these applications, and we can continue to advance Moore's law at the rate that it was promised, at the rate that we had relied on, basically, if I could just summarize it, to approximately 10 times every 5 years. Every 5 years, it would improve by another factor of 10. Every 5 years, it would improve by another factor of 10. In 15 years, the deficit of Moore's law no longer continuing to advance is 1,000 times. You just got to imagine what 1,000 times give you. 1,000 times of almost anything. And we're going to put some of that into perspective today. But 1,000 times. And this is the promise of GPU computing. Because we do computing in a fundamentally different way, and we rely on a large number of transistors, not faster transistors, but large number of transistors. And because we optimize each and every application with a specialized function, with a specialized processor, and the invention of CUDA made it so that developers all over the world and all different fields of science could access this form of computing. We've been able to accelerate applications, in fact, far faster than Moore's law. Well, deep learning researchers discovered that, and they realized that using our GPUs, they could overcome this handicap that deep learning had. Incredible effectiveness if trained on a large amount of data, which requires trillions and trillions of operations. Well, this GPU here, this is the Nvidia Volta GPU. This is the most advanced processor the world's ever done. Imagine nearly 10,000 engineer years to design this one chip. Several $billion of R&D. The largest single processor the world has ever made. The Nvidia Volta. 21 billion transistors, all effectively put to use. There's just no way to build a microprocessor that's 21 billion transistors large, because you run out of ideas. You don't need that many more transistors. The only way to make that CPU go faster is with higher clock speeds. That's not true with GPU computing. we could apply parallelism in a very specialized way to solve algorithms that are very important to researchers and scientists. So this is Volta, 21 billion transistors, and a whopping, staggering 120 teraflops. Well, to put 120 teraflops into perspective, that's effectively 100 CPUs. This right here replaces essentially a whole rack of computers. And I'll illustrate that more in a moment. So the end of these two factors, these two forces, the end of Moore's law and the emergence of artificial intelligence where software writes itself by torturing itself with huge amounts of data, learning effectively from digital experience. These two forces, when it emerged, turbocharged the adoption of Nvidia GPU computing. And the numbers show it. Over the last 5 years, the number of people who have attended GTCs around the world has grown by a factor of 10. The number of GPU developers has grown to 600,000. There are 600,000 developers in the world now who are learning CUDA from the several hundred universities all over the world that teaches CUDA, from the hundreds of textbooks that are written about it. 600,000 developers can surely develop amazing software for a few billion people to consume. So we've now reached critical mass in GPU computing development engineers. The number of people who downloaded CUDA, the number of times that it was downloaded in the last few years, almost 2 million. But the shocking statistic is this: half of it was last year. It took us 15 years to get here, and literally in 1 year's time, the number of CUDA downloads increased by a factor of 2. Well, the number of applications that we've been accelerating started out with only one in the beginning called NAMD, molecular dynamics. But over that time, if you take a look at the applications we now accelerate, of course, computer graphics. Computer graphics is a really rare type of application. This is the highest computing demanding application in the world that is also simultaneously high volume, because it's a medium for artistic expression. It is a medium for one of the most popular applications on the planet, video games. It is the medium by which hundreds and hundreds of millions of people enjoy their pastimes. It also happens to be incredibly technologically demanding. And so as a result, these two combinations, high computation intensity, technological intensity, and extremely high volumes came together to give us this propellant, this enormous R&D budget that allows us to fund the advancement of GPUs. There's actually not another processor that I know where the computational demand is simultaneously high and the volumes are absolutely incredible that continues to propel the development of that technology. Well, video games today not only look good, but the amount of technology inside, the simulation of the virtual reality, which is basically physics simulation, has really benefited many other industries. The first, of course, is scientific computing, the advancement of science. All of our lives are made better for it. Society is made better for it. In just about every single field of science that we know, whether it's quantum chemistry, material science, fluid dynamics, molecular dynamics, imaging, weather simulations, energy discovery, seismic processing, just about every single field of science has now benefited from the advancement of GPUs. And then, of course, deep learning. Our architecture is so pervasive, it's so accessible, that every single developer, every single deep learning researcher has jumped onto this platform. And then recently, even databases have been accelerated. SQL databases are going through a complete reinvention. If you could access video games as fast as you can on a PC, why can't you take the entire enterprise's data, put it into one computer, and play your company's database as you would a video game? And surely the developers who are working in these companies, whether it's MapD, Kinetica, Blazing DB, Scream Technologies, they've completely re-engineered the database. Now, the reason why the database is so important is this. If you can figure out a way to access the data and refactor the data and recreate its graph and its interactive, all of its relationships, your ability to analyze and seek out dependencies and relationships and correlations among all of the things that's happening in the world is dramatically improved. And as a result, on top of these companies, these amazingly fast databases, a whole bunch of analytics companies are starting to emerge. And whereas deep learning requires an enormous amount of data, many of us don't have as much data in any particular area in our company. And yet we would like to discover insights from them. They're traditional machine learning algorithms that have now been accelerated instead of requiring a high-performance computer or supercomputer to run your machine learning algorithms, whether it's clustering, k-means clustering, or generalized linear regressions, or gradient boosting, or support vector machines. All of these machine learning algorithms are now being accelerated on GPUs. And so from media and entertainment, scientific computing, deep learning, which is revolutionizing just about everything that we do on the internet, to enterprise computing and analytics, the GPU is now find itself with a rich, rich suite of applications that it accelerates. I think there's something like 450 applications now serving just about every important industry. The industries that we find ourselves in are some of the most important industries in the world. High-performance computing, of course. Internet services, of course. Just about every time you talk to your phone, just about every single query that you make, every photo search that you do, every recommendation that comes your way has somehow been accelerated by GPUs. We're in the process of revolutionizing the transportation industry. We've always been part of the design and simulation part of their workflow. Now we're inside the car. We also find ourselves solving one of the greatest problems, challenges in computing, planning. Imagine hundreds of millions of cars, hundreds of millions of people, and we got to figure out which car and which person to assign them to. Ride-hailing. Medical imaging, being revolutionized by artificial intelligence as we speak, and of course, logistics. Trillions and trillions of dollars of commerce are going to be revolutionized by artificial intelligence and robotics. We find ourselves solving some of the greatest challenges in computing today, solving the unsolvable for these industries. Well, our company is all about creating tools to enable the breakthrough of scientists, researchers, and developers. Enabling breakthroughs is the ultimate purpose of our company. We make tools. And so you could just imagine our delight when two recent, just last week announced, Nobel Prize winners, the work that they did, the revolutionary work that they did, that we were able to make a contribution to. One, the Nobel Prize of Chemistry, cryogenic electron microscopy. They could literally freeze the molecule in mid-motion and take a picture of it. Now, taking a picture of a molecule at atomic scale, whether it's an antibody or it's a virus, so that you can understand the mechanics of biology. Taking a picture at the atomic level, you've got to imagine how incredibly tough that is. And so these researchers, these international researchers, was able to do that using this technique called cryo-EM. And cryo-EM now makes it possible for us to understand biology and molecular biology at a level that nobody could ever imagine. If you could see something in action imagine our ability to understand it. 100 years ago, Einstein predicted that gravity was a wave. Well, as a result of the advances of some American scientists, Rainer Weiss, Barry Barish, and Kip Thorne, they detected the world's first, for the very first time, gravitational waves, a disturbance in the universe. Measured the slightest signal of a gravitational wave as a result of two black holes colliding. Because of our GPUs, they can reconstruct that image. Just about every modern instrument, whether it's the astronomic or the atomic scales, just about every modern instrument, scientific instrument, has a GPU in the back. And the reason for that is this. Just about every form of instrument, every form of measurement, every form of detection we know today, because we're trying to do it at astronomic and atomic scales, requires computation. Just about every single instrument is a computational instrument today. And without instruments, science can't advance. What you see can give you a great deal of insights. So from the astronomic to the atomic, now we bring you back to the human scale. Our GPU makes it possible for us to imagine being somewhere else. Well, one of the things that we do, of course, is beautiful computer graphics. And I'm about to show it to you. But today we're announcing a brand new product that's called the Nvidia Holodeck. This has been a dream of ours since the beginning of computer graphics. We've been pursuing this dream for a very, very long time. And today we've taken a very giant step. I'm delighted to show it to you. We combined several things in this holodeck. We think of this as the design lab of the future. We combined several things. Photorealistic computer graphics, of course. But once you go into a holodeck, into a virtual world, you would like this world to behave according to the laws of physics. If you touch something, you would like to know you've touched it. If you drop something, it should fall to the ground. If you lift something, it should seem heavy unless you don't want it to be heavy. It should obey the laws of physics. It should allow us to all be in there. You should be able to come into it. I should be able to come into it from anywhere we are in the world. Enable virtual collaboration. And then lastly, as we know, if there's going to be artificial intelligence in our world, there should definitely be artificial intelligence in the virtual world. And so we wanted to create this world, we call it the holodeck, this virtual world, where we can all be part of it. And so why don't I show it to you now? Guys?
Hey, Jensen.
Hey, Jensen.
Hey, Jensen.
Hey, guys. Sean, you're the one in the white, right?
Yeah, I'm right here in the middle, and I'm here with Lars and Igor.
Hello.
Hey.
Now, the truth of the matter is you guys aren't together. This is the benefit of Holodeck.
Exactly.
You could be almost anywhere, and we could network into it, and you can now have a shared experience in virtual reality. Now, ladies and gentlemen, what you're seeing here, of course, is going to be a little bit limited by the projector. When you get a chance during this show, I would love for you guys to try Holodeck yourself. The graphics that you're seeing, the graphics that they're seeing, runs at 90 frames per second. Okay? The graphics that they see runs at 90 frames per second. As a result, they can move at will inside this environment and feel really, really natural. They don't have to be in the same place. They could be in different rooms. They could be in different states. And most of the time, when we're back home and I'm enjoying Holodeck with them, the team is in St. Louis in another building, and yet we all seem like we're together. Okay, guys, show us what you want to show us.
Sure, just because it's a holodeck, of course, that means we can load in any environment that our imagination could bring us. So we've created this environment to do a study of another object. If we want to see something represented, we can bring it anywhere and really check out the design.
Wow. That's a beautiful lab.
It's certainly not bad, but Dominic, could you bring the car in for us, please? So, Jensen, I've seen the inside of your garage, and you're much more of a car guy than I am. So what do you think?
Well, I don't know.
It's pretty
How's it drive? The brand new McLaren. That's beautiful. Okay.
So, because the whole model is here, we just imported it straight from CAD. All of the details and materials are present in the design.
The leather,
the
carbon
steering wheel,
fiber.
everything.
Look at that. The rubber steering wheels looks like rubber steering wheels. The car paint. Everything is the original design. The benefit of this, of course, we're not trying to build a video game. We're trying to build a lab of the future. And so the lab of the future has to seem real. Here's what we imagine. Someday you're going to go into this lab and you're going to create a product. And you're going to have AIs helping you. And the AI could be handing you things. The AI could finish the job for you. For example, you might be able to design the basic shape of the car, and you say, you know what, I want to use off-the-shelf inventory that I've got in the company, and I want you to finish my car based on the inventory of parts that we currently have. And then the AI goes and finishes the job, comes up with the blueprints. You might also work with your AI to create the factory that's going to build this car. And so all the robotic arms and how they're programmed, and robotic arms are learning how to be robotic arms inside this environment, and you're helping it along. And so when you're done, not only did you design an amazingly beautiful car, you also created the entire factory necessary to manufacture the car. Okay, so that's how we imagine this as a collaboration tool, as a design tool going forward. So wow, that's just incredibly beautiful.
Exactly as you mentioned, we're able to go in and change designs and materials and really explore what this object's about. In this case, this McLaren's beautiful, but we can also take a look inside of the car in a way that would be difficult to do with a physical prototype.
Yeah, take this cool tool, Sean.
Thank you. So we can use this geometry clipping tool to go inside and take a peek through the engine cover into the engine itself and really explore the objects that we can see.
Wow.
And it's just a marvel of engineering.
Wow, amazing.
And of course, there's over 30,000 individual components represented in here inside of the holodeck with us. And we can explore all of them individually or take them apart.
That's every part. That's every part. Now, the thing that's really amazing is when you're in virtual reality, right now you're looking at it from a third-person view. But when you're in virtual reality, this car is going to look like it's sitting right in front of you. It's just utterly shocking. The idea of a clay model is going to be utterly unnecessary. And when you walk up to the car and you touch it in virtual reality, you're going to feel like you've touched it because there's collision detection, and with haptics, it would touch back to you. Okay, you've made a physical contact with that car. What else can you guys do?
So that's what we wanted to show you as kind of a sneak peek into the Nvidia Holodeck.
Now, when you guys are inside inside this virtual reality environment, you don't have to be in the same place, but you feel like you're in the same place, right?
Exactly. I'm right here with my buds.
Yeah, you guys look great. All right, you guys. Thank you very much. Good job. The Nvidia Holodeck. The original CAD designs, completely photorealistic. It's physically simulated, so based on the laws of physics, you really feel like you're interacting with the environment. It has virtual team collaboration. It doesn't matter where anybody is. You could put on your headset, come into that virtual environment, and you could basically have the benefit of virtual presence. And then lastly, with AI integrated into the system, you could create future AIs. And I've got some examples that I want to show you later. The system works basically like this. You could take your original CAD designs without changing it at all, as many piece parts as you like, the original CAD design, unmodified, because this isn't a video game. This is a design tool. You take that entire CAD database, you could add all kinds of materials to it if you like. You could add all kinds of materials and shaders and all kinds of other textures to it using Maya and 3ds Max, and then you import that directly into the holodeck. Now today we only support Maya and 3ds Max. However, this is a plugging architecture, and we're intending to support literally every single CAD package in the world. And on the other side of it, just to illustrate that, you could be literally anywhere. The Nvidia Holodeck. Early access is now. Go to our website, the nvidia.com/holodeck website, and register for early access. Okay? The Nvidia Holodeck. Super excited about that. Good job, you guys. Well, AI is the killer app, the new killer app of GPUs, whereas computer graphics was the killer app that really propelled our R&D and really propelled us over the course of the last 25 years. We've discovered a new killer app. And this new killer app, as a result of deep learning, is now being felt all over the world. The momentum behind the adoption of deep learning is really quite staggering. If you look at it from startups, with just a few tens of millions of dollars of funding, just a few years ago, 5 years ago, has now grown to $6.6 billion. The number of papers that are published around the world on deep learning has grown to 3,000 this year. Now, 3,000, the way to think about that is if 1 out of 100 researchers' work is worthy of being published, imagine the number of people who are doing deep learning research. And you could just see that in the Neural Network Conference, the International Neural Network Conference. NIPS is Neural Information Processing Systems, basically neural network artificial intelligence conference. Over the years, look at the attendees when they register. This year, long before, literally a month before the conference starts, a general purpose panic to register. I think only David Hasselhoff in Germany can attract this level of enthusiasm. Huh, guys? David Hasselhoff. He might actually be in the back. I'll just have him come on as a guest. So you could just see the adoption of deep learning and the momentum around AI. And the type of work that's being done just spans so many different fields of computer science and different fields of science. There's healthcare, enormous amount of research being done there. Robotics, enormous amount of research being done there. Natural language understanding. Speech recognition is taking the words that come out of my mouth, the sound, and translating it to text. Sound to text, speech to text. That's speech recognition. But what did I say, and what did I mean? That's natural language understanding. Natural language understanding, obviously, is much, much more complicated. A very deep area of AI, lots and lots of work being done there. If natural language understanding could be cracked, could you imagine how it's going to change the way customer service is done, how we interact with computers? Incredible, incredible opportunities. The number of research work is just really shocking. And people are solving these problems that we've, for the longest time, felt was impossible to solve. And so today I want to show you a few that are just kind of fun. It's easy to understand, and when you think about it, there's the oh my gosh moment. The first example is done at Nvidia Research. What's happening here is a form of computer graphics that's photorealistic but takes a long time. It's called ray tracing. We're simply literally following a ray of photons as it bounces all over the room, eventually coming into our eyes. Well, it takes a long time to literally trace each one of those photons, and that's why when you see those white dots and black dots, that's when the computer graphics is not complete. Well, we taught an artificial intelligence network how to finish the job. And the way to think about that is, if I showed you this incomplete picture, I bet all of you could figure out what is the best color to put into that dot. Somehow, we figured it out in our brain. Well, we taught a computer how to do the same thing, and it literally filled in the noise. Imagine what you could do with this thing. Using the same autoencoder architecture, you can now take an image that is very low in resolution and enhances resolution. From absence of information, we can create information that fundamentally breaks information theory. From the absence of information, we can create information, which is what's happening there. And so you can increase resolution. If you have a photograph that's ruined, parts of it was ruined, we can go back and fix it. Just by you looking at it, if you could figure it out, we can probably teach an artificial intelligence how to do the same thing. Here's another one.
Listen up. The train yard warehouses is our main objective. Alexei, you and your men will do that. You have to go in and out very quick.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
And so this is what's
The
happening.
avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
So this is what's happening.
Listen up. The train yard warehouses
If I could just get you to stop. So this is what's happening. Imagine lip reading. You learn how to look at the animation of somebody's face, and you could imagine the words that is being said. This is the inverse of lip reading. We had the artificial intelligence network look at a whole bunch of videos of somebody talking, and from it, it can now infer what is the animation of the face from the words spoken. What is the animation of the face from the words spoken? Okay? Like lip reading, except backwards. This one is called pose estimation. Pose is your 3D posture. How are you posed? How are you positioned in 3D space? Well, we have to teach, if you were to look at a video, you can probably infer what is the pose of that character in 3D space. However, how do you teach an artificial intelligence network to do that? How do you write software to look at a bunch of ones and zeros in a video and recognize where is the person and what is that person's three-dimensional pose from 2D to 3D pose? If we were able to do that, we can recreate that character in 3D world looking at the video. So shining a camera on top of me, I can now capture me and beam me into virtual reality. So imagine the holodeck next time. There'll be a video camera, just looking at me, and somehow I warp into this virtual reality world. Wrench is doing amazing work in pose estimation. This is really cool. This is a 3D animation character. This is a virtual reality character. And based on whatever you throw in front of it, it figures out what's the best way to animate, to navigate the course. You see what's happening? So it learned how to climb, learned how to hop off, all completely based on artificial intelligence. And smart enough not to walk into that. And as it tiptoes through this little tiny bridge, just like we would do. A virtual character taught AI. And then this last one, before I show it to you, it's a robot that learned from an example. This is Peter Abiel's work at UC Berkeley. He goes into virtual reality. He shows the robot how to stack bricks just a few times with just a few examples. This is what I want you to do. Stack bricks. And now, it doesn't matter where the bricks are located. Robot figured it out. One-shot learning, imitation learning, basically how we learn. So this is the actual robot stacking actual bricks, and this is how it learned it. in virtual reality. Okay, just some examples of what AI is able to do. None of these examples have we been able to write software to overcome for the longest time. Just imagine writing software to solve these problems. And now, finally, we use this artificial intelligence approach called deep learning. We feed it tons and tons of information, and somehow these deep neural nets learned. Well, the work that is being done in deep learning is literally all over the world. There are just so many researchers doing deep learning work, and we're just delighted that we are the deep learning platform for modern AI. There are all kinds of platforms that are being used, all kinds of frameworks and tools that are being used. PyTorch and Paddle of China, Chainer of Japan, MXNet that Amazon uses, Cafe2 that Facebook uses, Microsoft's Cognitive Toolkit, CNTK, Theano, and TensorFlow from Google. The number of industries that are advancing AI in research and now in startups all over the world. We're working with some close to 2,000 startups all over the world in all these different industries, all developing on the Nvidia platform. Now, our strategy and our commitment is to continue to advance with all of our might the ability to develop better, smarter, more complex AIs faster. Now, the reason why, even though we've advanced computing now, advanced AI research by a factor of 100 in the course of the last 4 years, we've improved performance by 100 times in 4 years' time. Deep learning has been completely revolutionized because of the GPUs. However, we believe that we need to improve the performance by so much more. And the reason for that is simply this. We want to make it possible for these AIs to learn how to write software itself, but to have AIs create AIs itself. And therefore, we need these massive supercomputers just churning away, trying all these different types of algorithms, and having software write software by itself. Just 2 weeks ago, just about the entire world's computer industry adopted Volta, our latest generation GPU. Volta is now available in every single cloud on the planet, from Azure to Google Cloud to Amazon Web Services, Alibaba, Baidu, Tencent. It's available everywhere, anywhere on the planet. As a result, all of these startups that are working on NVIDIA's platform no longer need to build their own supercomputer. They could go rent one in the cloud. And as they grow and their workload continues to increase, at some point they might decide to buy their own supercomputer, and every single computer company in the world now offers the Nvidia Volta GPU for their GPU servers. From IBM, HP and Dell, Cisco, Lenovo, and Huawei. Basically, the Nvidia GPU is everywhere. It's everywhere in every computer, every single PC, in every single region, available in every single cloud. And so we're going to commit to continue to advance this computing platform. The fact that we have one architecture makes it possible for your software development and for the company that you create to be able to enjoy growth every place on Earth. Using one architecture, using one singular architecture, you could develop on NVIDIA and scale out on NVIDIA all over the world. Okay? So the world's AI platform. Well, the next major challenge is after developing the AI, you have to run the AI. Developing the AI is called training. Running the AI, running the deep neural net, is called inference. To infer from input some insight about the future, whether it's classifying the image, recognizing things, recognizing voice. It could be predicting what future securities are going to be. It could be detecting fraud, somebody who is trying to break into your company. So these deep neural nets are trained on NVIDIA platforms. Now, the big challenge for us is to make it run incredibly efficient across all of the world's computing platforms. Now, this is an area that some people call IoT, but I see the world developing in 3 different ways. The first is that the AI network will run in the cloud. And these computers are massive in scale, 10 megawatts, 20 megawatts data centers, and they're running and inferring and basically running queries from billions and billions of people who are accessing the cloud at the same time. There's another class of device way on the other side that we're actually quite familiar with today. Things like Fitbits, Nest thermostats, your phone, all of these little tiny devices that have a little bit of intelligence inside. And that little intelligence network could be voice recognition, it could be image recognition, it could be recognizing your heart rate, measuring your blood pressure, measuring the tremor on a piece of equipment, and recognizing that that tremor is going to lead to failure in about a week's time. And so instead of waiting, when that machinery goes down, you might send somebody out to repair it in advance. And so it's called IoT, and I believe over time there'll be trillions of these devices. And then there's a class of machines in the middle. They're not exactly supercomputing clouds. They're not intelligent sensors, but they're autonomous machines. These machines need to operate and be intelligent and do smart things even when they're not connected to the cloud at all. For example, a self-driving car. You would really, really appreciate it if your car drove safely by itself, even without internet connection. It could be a drone that flies out to find somebody who's lost in a forest. It could be the drone inspecting pipelines, or going through and looking at a forest fire, or it could be somehow inspecting your plot of land and all the food that all the farming that you're doing, and looking for whether there's a disease that had broken out. It could be manufacturing robots. It could be these little drones that people are starting to develop for the last mile of delivery. As a result of the Amazon effect, where more and more of us are basically buying products online and hoping that it would be delivered to your house, the number of truck drivers in the world can't possibly serve all of us buying products online and hoping for it to be delivered that same time. And so companies all over the world are building these last mile delivering pizzas, delivering soy sauce in China, delivering a hamburger to your house. Okay, so autonomous machines. All of these are going to need AI inside them. And so the question is, how are we going to be able to support a world where you only have a few milliwatts of power on the one hand to something that has to be completely autonomous on the other hand, and then, of course, data centers. The number of different types of devices that we have to support is exploding. The networks that we're supporting is exploding. Starting with CNN. CNN's convolutional neural networks is a neural network that magically figures out what are the important features that represent a particular object or a particular pattern. And it has this ability to learn the features by itself and to generalize that information so that even if you change the color, the shape slightly, the orientation slightly, it still recognizes it to be the thing that it learned. So you could have a cat be partly occluded, and it still recognizes it. You could have a cat change colors, wear a hat, and it still recognizes it. The recurrent neural networks learn sequences, speech, etc. And this one is the revolution that came out recently from Ian Goodfellow. He created this thing called the generative adversarial network. You have one network that's trained to be a master detector. You have another network that's trying to fool this master detector. These two neural networks, one of them generating fake ones, the other one detecting the real ones. So it could be an piece of art, for example. One network generating fake art, fake Picasso, while the other one has been trained to recognize real Picasso, and because the two of them are competing against each other, one trying to fool it, the other one trying not to be fooled, and as they learn and learn and learn and learn and learn and develop over time, one becomes just amazing at recognizing Picassos, the other one becomes amazing at generating Picassos. Two networks, now incredibly powerful, the adversarial network. And then lastly, the recurrent neural net, the reinforcement learning neural net that was used by Peter Abel, and this is basically trial and error. The network is trying over and over again, randomly, initially. Every time it tries, there's a value function that determines whether it's doing it well or not so well. Whenever it does it well, it's encouraged to move in that direction. If it does not so well, it's encouraged to move away from that direction. A value function determines that. Reward and punishment. Recurrent neural networks is how we're going to use, is the basic method for us to train robotics. Explosion of the type of networks. The number of, and this is just a brief view of it, there are so many different designs and so many different architectures coming out. Well, the complexity of the network is growing as well. This little tiny dot, this complexity chart, the size of the area of the circle, represents the number of operations times number of operations, and I just simply multiply the two of them together, number of operations times the amount of memory that it has to access. Okay? GOPS times bandwidth. That little tiny dot is the original AlexNet just a few years ago that beat every single computer scientist in the world in image recognition. That's that little tiny dot. That little tiny dot, overnight, without learning how to do computer vision, learned computer vision fine enough to beat every single computer vision algorithm expert on the planet in one ImageNet. Completely revolutionized computer vision. If it wasn't because of ImageNet, the work that we're doing here in self-driving cars and robotics wouldn't have nearly progressed as fast as it has. And yet, look at that. Over the course of just 4 or 5 years, it has grown. These networks have grown 350 times. This is a speech network. Has grown 30 times in the last several years. This one's really exciting. Language translation. I really believe that in a few more years, I'll be speaking into this microphone in English, and it will come out in German. And it will do it completely in real time. And so as a result, that Star Trek Universal Translator is about to happen. The Neuro-Machine Translation Network. Goes in English, comes out German. The network complexity has grown so much. And so what we've done is this. 2 weeks ago we announced a new type of optimizing compiler. It takes neural networks in, and it uses advanced compiling technology and optimizes the network for all of the target devices that it would run. Some of the target devices are very high performance GPUs like the one that I showed you, Volta, 120 TOPS, 250 watts, powers the data center, all the way to something that's a self-driving car, to a little neural network that goes into a little robot we call Jensen, just a few watts. It takes input from any framework, any architecture of network from any framework, runs it through this optimizing compiler, and it targets machines that ranges all the way from several hundred watts to several hundred milliwatts. The Nvidia Tensor RT 3.0. It basically does this. It takes this neural network that's incredibly complicated, this is just one layer, and all the math that goes through it, and we do weight and activation precision calibration first, and then we fuse the layers. Some of the layers could be combined together. Some of the tensors could be combined together. Some of them could be eliminated altogether. And so we fuse the tensors. We do kernel optimization with dynamic programming, tracing almost every single path to figure out what is the single best path for optimizing the speed and the size and the accuracy all at the same time. And we also, of course, have to support multiple streams because sometimes the machine has multiple cameras. Well, the result is pretty amazing. So that's what it does. And this is how well it does it. And so, if you take the CPU, we train the neural network, which is done largely on Nvidia GPUs today. However, once the network is trained, it's largely run on CPUs today. And the reason for that is because the entire world's cloud is powered by CPUs. And so you train that network, the ResNet 50, now this is 50 layers deep ResNet. The CPU plus TensorFlow, which is Google's framework, runs at 140 images per second. Without TensorRT, without this optimizing compiler, the output of TensorFlow, as we move it into this Volta V100, this GPU here, this does 300 frames per second. However, if you optimize it with TensorRT, all of a sudden the performance just skyrockets, 5,700 frames per second. Because TensorRT optimizes for CUDA and optimizes for the architecture of our GPU, takes advantage of the instructions that we put in here, called Tensor Core, which is optimized for deep learning. For open NMT, neural machine translation, basically language translation, four sentences per second to 25 without TensorRT to 550. Okay? But this is just one dimension of the speed up. 40 times speed up in imaging, 140 times speed up in language. But when you look at the latency, how long it takes in addition. First is how many you could do at the same time. The other is how long does it take for you to do any one of them. In the case of images, we halve the latency. In the case of language, 100 milliseconds versus several hundred milliseconds will make all the difference in whether you can talk to a computer or not, having a reasonable conversation. So, TensorRT3, our brand new optimizing compiler. Now, what does it look like in a data center? This is what it looks like in a data center. So suppose you had no GPUs in the data center, no TensorRT. This is 160 CPUs. 160 CPUs will do 45,000 images per second. And this is basically what's happening in the cloud today. Whenever you ask for a photograph, whenever you upload a photograph, this is essentially what's happening. Every single one of those transfers go through some kind of a deep neural network, and it's run on a CPU cluster like this. In this case, 65,000 watts. So 1,500 watts per rack, 4 of those racks. About $600,000 without cables and the top of rack switches and all the power supplies, about $600,000. And this is what it looks like if you bought a GPU. I know, I practically fell out of my seat. You see this? Before, after, before, after. The more GPUs you buy, the more you save. Just think about that. The more you buy, the more you save. 1/6 the cost, 1/20th the power. 1/20th the power. This will improve your total cost of ownership a factor, an order of magnitude. Before, after. This is the best demo in the world. This is the best demo in the world. This is the only demo that IT department goes, here, do that again. Our IT department goes, oh, Jensen, I love that. I love that. I'm going to make that a screensaver. Just go back and forth, just like that. My kids always, every time, my kids know how cheap I am. They call this save the money. Just one money, save the money. This is save lots of the money. Okay, so that's what it looks like at a data center. But let's take a look at that. Let's look at that in real time. What does it really feel like? Okay, so this is what inferencing is. Now, the thing is what's really remarkable about deep neural nets is this. This is what you see. What the computer saw was a whole bunch of ones and zeros in 3 different layers, R, G, and B. They're just a whole bunch of ones and zeros, a whole mess of them. And somehow from that whole mess, that's not a cloud. From a whole mess, that's not a beetle. From a whole mess, that's not a cactus. And that's not a butterfly. From that whole mess of ones and zeros, somehow it's got to figure out what these things are. And so, Ryan, why don't we show them?
Sure. Here we go.
Okay, so this is what's happening. This is inference on a CPU. And you could see up there where...
Oh, it's in the corner.
Up in the... So it's running on a CPU. It's doing 4.8 images per second. But what are these flowers, though?
Oh, let's have a look.
That's a sword lily. Okay?
There's a bird of paradise.
All right. I believe it.
Moon orchid.
That's a moon orchid. Okay. That's what?
A daisy.
That's a Peruvian lily. Okay? Lots of lilies. A Lenten rose. A sad flower. Oh, I bet that one smells good. It looks like it smells good. This is okay, that's what it looks like. A Japanese, what?
Anemone.
Okay, ruby-lipped cattle. That was a cow?
I don't know half of these.
Blanket flower. Okay?
Bougainvillea.
So, guys, the computer saw a bunch of ones and zeros, and it classified these images to be those things. Now, here's my theory. 100% of you failed it. I wouldn't have called any of them. I would have just said flower, 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 flower. That's a flower. That's still a flower. You see what I'm saying? That's a cloud. I don't know what that is. That's an animal. That's Christmas. That's, right? And so 100% of us would have failed it. And here's this computer looking at ones and zeros, figuring it all out. Utterly superhuman. Imagine applying this technology to medical imaging. Imagine applying this technology to self-driving cars. Imagine applying this technology to robotics. We can finally write software that allows software to write itself so that it can solve the otherwise unsolvable. Well, the problem is 4 images per second looks fast here, but if 1 billion of us are using it, that's going to be a data center so large it will melt icebergs. And so obviously we can't do that. And so Ryan, show us what joy looks like.
Sure.
That's 1 GPU. And so this is the difference between the fastest CPU in the world versus one of these babies. Now that's a fast car. Okay, here in Munich, here in Germany, this would be a supercar right here. Look how fast that is. I just hope it's still right. And so these GPUs, that's a California poppy.
I'll find
a yellow iris. Okay? So this is what it looks like on a GPU with TensorRT. Incredible speed up. $500 162. In this particular network, we sped it up 100 times. This GPU has replaced 100 servers. That's the shocking amount. Imagine all the money you're going to save. Run out and get one right away. Okay, so that's for images. Let's take a look at another one. Well, and so the next one is a technology that's done by, based on a technology by DeepGram. They're a startup company. They're a startup company in Silicon Valley. And what they've done is this. They've taken basically sonic information and they mapped it into a computer graphics, into an image, and they use CNNs, use image recognition on sound information, and as a result, their deep learning voice recognition is not only incredibly accurate, it's also incredibly fast. Their application is for companies who are with customer service, or they need to make sure that all of the transcription or all the phone calls are done within regulation. It could be in healthcare, it could be in finance, it could be in law, it could be in customer service, hotels, it could be retail. So many different types of companies in the world that can't afford to do voice recognition in the cloud. They have to do it inside their company. And not only that, they want to have the ability to retain the data, the observation from all of the speech, so that they could apply that information to other AIs to enhance their business. And so the thing that DeepGram does is a voice recognition engine that is just lightning fast. Now, the thing that's really great is this, and so we created this demo. It goes so fast, so super real time, that you could literally watch any movie and search for words. Just search for the sound of those words. It's going to listen at super real time. It's going to watch and listen at super real time a movie and find whatever scene we need. Okay, so Ryan's going to show you that. Go ahead, Ryan.
So you might have gathered what we're going to show today. So this is we've transcribed a whole bunch of Game of Thrones, and now we can just go and search through it. So we can find our favorite scenes. No one will take my dragons.
This one's really cool. Is Monty up here? Hey, Monty. So the folks at Columbia,
Cambridge Consulting.
Cambridge Consulting. Yeah. Why did I have Columbia in my head? Cambridge Consulting created this incredible artificial network. And Monty's going to tell you about it in just a second. But we're going to run it so fast. The inference is done so fast that this artist, this trained artist, is going to be able to collaborate with you. So Monty, first of all, tell us what you guys did.
Sure. So this is Vincent here. It's a combination of many different deep neural network technologies using generative adversarial network technology, but several of them combined. Those processed 8,000 masterpiece artworks from Western art from Renaissance through to current day. 8,000 is nowhere near enough traditionally for deep learning to do anything useful. We're going to generate megapixel images here, and you would estimate we should need at least 1,000 times as much. But because of the generative adversarial nature, this challenge that Jensen spoke about between different networks competing and improving each other, we can squeeze so much more out of the data than might traditionally be viewed possible.
And so just very, very simply, Monty and his guys has trained this network how to basically draw, how to generate art like the great artists, okay? How to draw. And they use this GAN network to basically learn how to draw. And then they used another network. There's 7 different networks, but the other network that they have to create is something that would enhance the resolution of the drawing so that it's many megapixels, so it looks beautiful. Okay, and so why don't you show it to us?
Oh, okay, I'll give you a short demonstration. So if I were just to touch the pen onto the surface, initially we get kind of random noise. There's no possible way you can guess what I'm trying to draw there.
That looks like art.
Inherent in the network. That's 8,000 artists all merged together. But if I sort of went for perhaps a kind of jagged landscape, something like that, you can see in real time as I do that, it's beginning to perhaps color in. It's getting a hint that the sky is unlikely to be rock colored. I can begin to draw more detail. It comes through more clearly like that. It's a very, very simple picture. And for example, I've got a couple. It's going from the yellow lines, but I drew a better one earlier that looks a bit more like that. And what's interesting there, if I bring the lines up for you, you can see very, very simple sketch. So this isn't recognizing objects. This doesn't know that it's it hasn't been trained just on landscapes. If I go and do something damaging to the picture, you can see it's completely changed its mind on what that is. That's no longer a landscape. And even if I add some kind of super real detail like that moon there, we've now got more of an illustration out of it. It's the same picture. I can go between these two.
Hang on a second. I could do this.
Yeah, go on.
All right, so I could be an artist.
Please.
So how do I delete that?
Clear, yeah. Get going.
Delete that? Okay. All right, so...
I think you can see how fast the inference is running here. So this trains overnight on a DGX1 supercomputer. It takes about 14 hours, but it's now running, sort of real-time frame rate inference on a small box here. We've also trained the network with slightly different parameters. So one thing we can try are some slightly different styles.
So that looks a little bit like Picasso, right?
Absolutely.
Got to sign that.
Yeah. Wow.
JHS right there. Okay. That'll be $1,000.
Press the heart.
All right, let me just do one more.
Let's try a few of those different networks, perhaps.
Okay.
So there's some that'll see that perhaps as a lino print, or that have seen more modern pieces.
Wow.
More colourful.
That's fantastic. Look at that.
The effect.
Incredibly fun. Okay, good job, Monty. Thank you. Thank the guys for me. That's so amazing. All right, so you saw some examples of us using deep neural networks to solve problems that otherwise would have been unsolvable in the past. We created a platform that makes it possible for researchers and developers to train their network and develop their network wherever they are. It could be in the cloud, it could be in their data center, it could be on their computer. We created this new TensorRT optimizing compiler that targets the entire range of all the processors that we make. And as a result, sped up deep learning inference by a factor of 50, 100, 150, as a result, saving enormous amounts of money. Well, creating this deep learning network and solving unsolvable problems has led us to solving some of the most challenging and most exciting, and in our belief, the most transformational opportunities in the world. Transportation, as you know, is an enormous industry. It's the fabric of society. It makes it possible, it gives us freedom, makes it possible for us to get around, of course. Two fundamental technologies has now inspired car designers all over the world to do amazing redesigns of what's possible in the future. This is one example. This is the work that is done at Airbus. But if you could imagine, the wing is autonomous. The wing is completely autonomous. There's an autonomous machine inside the wing, and it's a battery-powered wing. The car is autonomous, and it's an electric vehicle. If you want to have a flying car, you simply summon your wing. The wing flies to you. You get disconnected from the electric drivetrain. The wing picks you up. And holy cow, imagine the experience. And so people are starting to think about these ideas. People are starting to think about these ideas. From the extraordinary to figure out how can we revolutionize transportation for the last, for the 50-mile range, which is what this is intended to do, to every single day's transportation. And so what we did was we applied ourselves to create a driving network, a driving platform, and create a platform by which the entire transportation industry could adopt to create autonomous vehicles. Our driving platform consists of several layers. The first layer, of course, is the computer. The way you compute for an autonomous machine is fundamentally different. Second is an operating system that allows it to take information at real time from all the different sensors and process it. And algorithms and libraries we call DriveWorks that exposes the capability of the computer to applications on top we call Drive AV for autonomous vehicles. And the type of algorithms and the type of applications we have to develop is basically in three categories. One, you have to figure out where you are. It's the perception networks. Where are you in the world? Where's everybody else around you? What do you sense? The second is localization. Based on everything that you sense, you have to figure out where you are, where everybody else is, where they're moving to, and track everything around you. And then third, figure out, based on all of that, reason about what to do. You might have to stop, you might have to divert, you might have to turn, follow a route, accelerate, pass another car. There's a whole lot of different actions that you could potentially take. And so we created this platform, this complete platform that is basically drivable. Several thousand engineers at Nvidia are working on this. This is an open platform. It is fully functional safe when it's done. It is auto-grade. And it employs three fundamental computing approaches. One is deep learning, another is computer vision, and then the other is parallel computing. We have to do these algorithms in a whole lot of different ways, and the reason for that is because we want diversity. These cars are going to allow us to not pay attention and still drive us safely. But if something were to happen, it could be a systematic problem, something in the algorithm. It could be a computer failure. Maybe it just got old. Maybe it broke. Maybe it got bumped into. Even if the computer failed, and even if the algorithm failed, we still have to have a backup that allows us to drive the passengers to safety. Just imagine that. How do you create a computer that when it fails, it still operates perfectly? And so the answer, of course, is both having redundancy as well as diversity. We have to solve the problem. We have to solve the same problem in multiple ways. We have to solve the same problem in multiple ways. One simple example is this. One way for you to avoid hitting something around you is recognizing and detecting everything around you and figuring out where they are, and then simply driving where they're not. Okay? Figuring out where everything around you is, and then driving where they're not. The other way of solving that problem is to teach a neural network to recognize where is it safe to drive. So one way is to detect what is not safe. The other way is to detect what is safe. If we have these two basic approaches for perception, then that provides us some amount of resilience. Algorithms like this over and over again are stacked all over this computer so that we can provide redundancy and resilience. Well, let me show you a home movie. The engineers are working really hard, and the car that we integrate all of this into is called the BB-8. And they're driving all over California, all over the East Coast. There's some 20 cars driving around. And we made a home movie for you. Let's play it now. We created the stack so that we can understand how deep learning works, so that we could help the industry solve one of the greatest challenges in the transportation industry. And then this platform is completely open. You could use all or parts of our platform, whether it's calling on the libraries that we have, developing the libraries completely yourself, programming directly to CUDA, or using our autonomous vehicle applications that sits on top of it. One of the areas that is going to revolutionize society in just an incredible way is ride-hailing. You guys know this very well. The utility of a car is dramatically higher. The convenience of moving around is dramatically higher. More and more people are moving into the urban areas, and so it's less and less convenient to own their cars. And so we see, all of us see, this revolution that's happening with ride-sharing or ride-hailing. The number of companies that are working on the next generation autonomous vehicle transportation services is just all over the world. There's just some really, really exciting work that's being done. Here in Germany, Audi, the work that's done by Daimler. In the United States, Uber, Lyft, of course, Waymo. In China, Baidu. Ford with Argo AI. GM with Cruise. Startup called Zoox, doing really great work. Nutonomy in Singapore. And Yandex in Russia. Just about every single geography in the world, companies are trying to figure out how to make these cars completely drive by themselves without a driver inside. Which basically means this. In the worst case scenario, if a car computer were to fail, the algorithms were to fail, the backup computer will have to complete the mission. The backup computer will have to complete the mission. Even if a sensor were to break, even if somebody were to bump into your rear and somehow dislodge the sensor so it's no longer calibrated, you still have to finish the mission. Because otherwise, you would have to say in a very gentle voice, "Get out." You would have to tell the passengers to get out because there's nobody driving the car. You can't take over, there's no steering wheel. And so the level of computation that's necessary to solve this problem is just enormous. And so just to give you a sense, this is a level 2 sensor suite with cameras and radars. And here's a level 5 sensor suite. It has cameras and radars, a lot more of them because they're all completely redundant. And then there's LiDARs that are surrounding this car. This car is just packed with sensors. If you think about the work that it has to do, it has so much more resolution because it has to see further, it has more redundancy that it has to do deep learning on. It's got all these surround LiDARs that has to do point cloud processing. These cameras and LiDARs have to localize in a redundant way. They're tracking all of the objects around the car because it's likely this car is driving in urban areas and there are people crossing the street. These cars also are mapping cars because it's got to update the HD map that the car is driving within as the roads change. There's no driver, and so every single time it has to have complete confidence that it can complete its mission. It has to have enough horsepower so that the path planning and the controls of the car is as smooth as possible. It turns out that in the old world, high-performance engines makes cars smoother. Smoother for acceleration, smoother at idle, smoother at cruising. In the future, the more computational performance you have, the smoother your ride will be. Okay? There's a very similar analogy there. And then, of course, sensors and computers has to be fail-operate, and this computer has to have enough capacity for software to be added to this car. Hundreds of software engineers are developing these cars at the same time. We simply can't guess accurately enough how much computational capacity is necessary. And so this is what they do. This is what it looks like in the trunk. Brand new AI. This brand new AI is an SDK we call Drive IX, Intelligent Experience. We've basically done this. We've fused the AI that drives the car and all the perception layers that senses what's around the car with an AI that's in the car that senses you, the driver, and all of the passengers in the car. The sensing, the perception of what's around the car and what's inside the car, and some basic neural networks that we've already pre-trained to track where your eyes are gazed, where your head is posed, read your lips, understand your words, all of those type of capabilities, gesture recognition, combined with the perception of what the car sees, okay? The combination of that, the fusing of that, is going to allow our customers to write applications that are really quite magical. You'll literally be able to walk up to the car, and the car knows exactly who you are. And it already adjusted the seats, opens the car, and if you're a passenger, it knows who you are, and it adjusts the seats and changes everything according to your desires. You're walking up to the trunk because you're carrying a whole bunch of bags. It recognizes that you just went shopping. It's you. That food is going to end up in your trunk, which now has plenty of space because of Pegasus, and you're going to put your food in the trunk. Okay? And so all kinds of different scenarios are going to be possible. And so this SDK is going to be available in early Q4 and basically runs on our Drive platform. And as a result, hopefully these cars becomes an AI. Your car is an AI. Okay, so it's an AI car. It knows who you are, understands what you like, it recognizes the situation around you, recognizes that maybe you're dozing off and you shouldn't be. Maybe you're not looking in the direction of some kids playing in the street, and it warns you, says it to you nicely, that you should be looking to your right. Okay, whether it's in autonomous driving mode or not in autonomous driving mode, your car AI will look out for you. Creating the car computer is just one of the extraordinary endeavors that these companies have to take in order to create the autonomous vehicle fleet of the future. It is an absolutely extraordinary undertaking. Software development like it's never been done. Computer deployment like it's never been done. The amount of software we're writing, the amount of AIs we have to develop, and the fleets that are going to be tested all over the world is an extraordinary undertaking. And it has a lot of different pieces. Today, I just wanted to show you what it takes to build this self-driving car. Not just a prototype. Building a prototype is fun and easy. But getting ready to deploy the fleet is incredibly hard. First of all, you've got to collect a whole bunch of data, and you have to label them just perfectly for every single country, every single road structure, every single road condition. You do it because it's so important, and you do it because you can. We have hundreds of people doing this at NVIDIA. You take that network and you train it on the supercomputer that we designed. This supercomputer here is called the DGX, and this GPU goes in here. This GPU goes in here. Can we see it? Can you guys see it? Okay. I can't see you guys seeing it. But this is one of the GPUs. There are 8 of them here. 1 petaflops. 1 petaflops. So that's basically a whole wall of computers fit into this one NVIDIA DGX. This DGX is used for training the network. Okay, so we use it to train the network and run training on DGX. But there are so many road conditions, so many scenarios, we simply can't collect data on because we like not to. We don't want to simulate somebody jumping in front of your car at the last moment. There's no sense doing that, and so we decided to create a 3D simulation. Imagine harnessing all of NVIDIA's capability in photorealistic rendering, and we created a simulator for the car to try all of these different scenarios that otherwise would be impossible to do. We call it 3D Sim on DGX. I've already shown you Drive AV on DPX, Drive PX, and then lastly, ReSim. ReSim is a gigantic undertaking, and here's the reason why it's so important to do it. Every single time you update your network, before you put it on the road, you would like to know that it's going to pass in simulation all of the roads in the world. All of the roads in the world. And over a period of time, we're going to collect up enough data, enough videos, for literally every single road in the world. And so we call this super real-time simulation with DGX. And using the new TensorRT 3, this is what we can achieve. With just 8 NVIDIA DGXs, okay, so this is a picture of our Saturn V supercomputer. The reason why they're all intermixed like that is because each one of our DGXs consume about 3,000 watts. Okay, that 3,000 watts, of course, replaces a whole wall of of servers, and so we're delighted by that. But we still need a whole bunch more in order to simulate the world. And so each one of the racks consists of about 20,000 kilowatts, 18,000 watts, and that allows us to hold about 6 of them. And so what's going to happen is this. We collect miles and miles and miles of road data, and in this case, 300,000 miles we can simulate on 8 of those in 5 hours. 300,000 miles represents 10% of all of the paved roads in the United States. All of the paved roads in the United States. And so basically, if you could simulate that in 5 hours, we could simulate every single paved road in the United States in basically 2 days. So when we finally develop our software and we want to release it, we can simulate the whole thing in 2 days. Now, of course, that's if you're perfect. The whole point about simulation is to find bugs. And the whole point about finding bugs is sometimes you do find them. And so we have to do this over and over and over again. And that's one of the reasons why we have so many of them, so that we could reduce the resimulation time down to essentially hours. Let me show it to you. Hey, Justin, this is basically us running in real time. This is running on one Drive PX. One Drive PX is doing a really great job. It ignored the wiper, snowy road, recognizes all the pedestrians, the signs. It's doing a great job detecting things, detecting the road. Okay, now let's go to, suppose we want to do this on our DGXs. And this is what's happening. And this is how we take a brand new network, the entire software stack, and because our architecture exactly compatible between Drive PX and DGX, the supercomputer and the car computer is architecturally and software compatible. We take the software stack, we put it on DGX, and we run it at super real time. Okay? And so thank you. Thanks, guys. Good job. And so that shows you, give you a sense of what it takes to create a self-driving car. From the training of the neural network on a supercomputer, to the simulation of extreme cases on a supercomputer, to driving on a supercomputer, to testing on a supercomputer, that entire flow is extraordinarily computationally intensive. And so we've plumbed this entire platform end to end, and it's open to our partners and developers all over the world. There are now 145 startups working on the NVIDIA platform. They're building trucks, they're building shuttles, they're building cars, some of them level 4, some of them level 5, some of them for long haul reasons, some of them for the last mile. There are autonomous machines coming from just about every corner of the world. Everything that moves in the future will be autonomously assisted. Some of them will still have drivers, but all of them will have AI. And so hopefully it will be a lot more efficient in the long term, and transportation is going to get reinvented. I mean, there's just some really, really cool things. Mapping companies that are using our platform, they use our cars for mapping, and they use our platform for map generation. So, autonomous machines. The next generation of autonomous machines is super exciting. Let me finish by talking to you about one of the things that we're working on that's super exciting. And this autonomous machine is unlike the autonomous vehicle. And the reason for that is the autonomous vehicle is designed for collision avoidance. Autonomous machines are designed for interaction, which means they largely collide. collision is one of the most important things that autonomous machines do. Well, we can't afford to have these autonomous machines learn how to interact with the world by being in the world. And so there are two fundamental technologies we have to create. The first is a whole new type of processor. We call it Project Xavier. Project Xavier is in the process of being taped out. We'll have silicon here pretty soon. It fundamentally changes how computing is done. It's really about real-time sensors. It's really about computing in parallel, using computer vision, using sensor fusion, using deep learning. And it has to be incredibly energy efficient. 30 teraops of operations in 30 watts. That's the first piece. The second piece is a simulation environment. We need to create a world, a virtual world, where robots can learn how to be robots. They go into this world, and they use reinforcement learning, and they try it over and over and over and over again until they finally figured out how to be a productive and useful robot. Basically, there are three different things. We have to train the network just like we do with the self-driving car. Then we put that network into a virtual environment where the robot is in, and that virtual environment is powered by a supercomputer, so it could run at super real time. And when you're done with that network, then you could put it on this processor we call Xavier, jack the AI right into the head, and this robot will literally stand up and start walking. That's our goal. And so in order to make this happen, there are two pieces of technology we have to create. One is Xavier, and one is Isaac. We're going to show you Isaac real quick. Guys, this is the Isaac world. This is Isaac's lab. And this is Isaac learning how to play hockey. Now, you could see Isaac has two eyes, and those two eyes are basically deep learning eyes. So Isaac's world is accelerated AI because Isaac has to have AI to start. It has to be able to recognize, perceive the hockey stick, perceive the puck, perceive where the net is, and then it's got to figure out somehow, without us writing any code, what to do. And we gave it a value function, and the value function basically says, if you put the puck in the net, that's good. If you don't put the puck in the net, try again. Okay? And so we allow it to try and try and try. Notice it's doing it right now. It's learning how to, it's learning right there. Now, in order to speed this up a little bit, Gordon, is that you back there?
Yeah, we're just going to switch to full screen, and then we're going to switch to a robot which is trained a little bit more. So the robot we just saw there, it learned to basically hit the puck, and no more than that. And then we've got another robot, which we've trained for a little bit longer, and this robot's learned to hit the puck. It's just further along the training program. And now it can hit the puck, but it's not very good at getting it in the goal. So to speed up the learning even more, what we really want to do is train it in parallel and learn the aggregate experience of lots and lots of robots.
And so Gordon, here in this case, what's happening is we replicated Isaac, and we let them all train, and then we stop it at some point. We take the smartest Isaac. We take the smartest Isaac, and we put the smartest Isaac in everybody's head. And then we start all over again. Okay, you rinse and repeat this over and over and over again, running on top of a supercomputer. And all of the Isaacs, they see the puck, they see the net, they see their stick, and they have to figure out how to sync it. Now, ideally, if this world looks like our world, ideally, when we're done, we could literally take the AI that's in Isaac in the virtual world, put it in the physical Isaac, and the physical Isaac will recognize exactly what to do and do it. Okay? All right, so let's, how about one more example?
So this is Isaac as trained as much as we could get. He's quite good at getting it in the goal. He's not absolutely 100% perfect, but he's pretty good at playing hockey, and his swing is much more convincing, and he's pretty good, yeah.
All right, not bad. Good job. Okay. So autonomous machines, the next adventure for our industry. And we're seeing so much excitement around Isaac. Every research organization we go to, they can't wait to get their arms on Isaac. So we're looking forward to releasing it in the near future. Okay, so today we talked about several things. We announced the Nvidia Holodeck, the design lab of the future, fusing some of the most advanced technologies in computer graphics today. Photorealistic rendering, virtual reality, physically real simulated environments, and artificial intelligence. The second thing we talked about is Nvidia, the AI computing platform, and how we have established ourselves in AI, put our AI platform all over the world, in every single cloud, in every single data center, and recently we announced TensorRT 3, which allows us to take these networks that were trained on these platforms to run in real time with super levels of efficiency. The third thing I talked about is the NVIDIA Drive. The entire vision of Drive is far more than building the chip. It's the chip, it's the operating system, it's all the libraries and algorithms and all the applications that make it possible for autonomous vehicles. However, it also includes developing the entire software stack for a fleet of cars that we would like to deploy in the near future. And then fourth, I talked about the NVIDIA Drive PX Pegasus, the world's first computer that is able to allow all of these robot taxi developments happening all over the world to go to production. And then lastly, Project Isaac, our AI world for robots so that they can learn how to be robots. Ladies and gentlemen, I want to thank all of you for coming to GTC. It's going to be a really great GTC, looking at all the papers that are here. This is a brand new computing era. The work that we're doing is just so exciting. The computer industry is now able to solve problems that historically was not solvable. Thank you for coming and have a great GTC.